Hi, my name is Izzat Iskandar bin Safarin, metric number DD1779. For my parts in torsion test experiment, I will explain about additional theory and result. Torsion is the twisting of an object due to an applied torque. Torsion is expressed in either the Pascal and SI unit for Newton per square meter, while torque is expressed in Newton meter. Torsion test: twist a material or test component to a specified degree with a specified force or until the material fails in torsion. The twisting force of a torsion test is applied to the test sample by anchoring one end so that it cannot move or rotate, and applying a moment to the other end so that the sample is rotated about its axis. The purpose of a torsion test is to determine the behavior of a material or test sample exhibit when twisted or under torsional force as a result of applied moment that cause a shear stress about the axis. Measurable values include the modulus of elasticity in shear, yield shear strength, torsional fatigue life, ductility, ultimate shear strength, and modulus of rupture in shear. These values are similar, but not the same as those measured by a tensile test, and are important in manufacturing as they may be used to stimulate and service condition, check the product's quality and design, and ensure that it was manufactured correctly. This is the example of common test standard of torsion test, and this is the common application of torsion test. This is the result that we get in the experiment that we do in the lab.
Assalamu alaikum. My name is Muhammad Amar bin Muhammad Abdul Wahab, CD180130, and today I will talk about observation in lab torsion tests. Okay, there are a few observations that we can see through this test. First of all, is the brass shaft specimen is gold in color, whereas the mild steel shaft specimen is silver in color. That is the first one. The second is the brass shaft specimen is longer than the length of mild steel shaft specimen. Okay, the third is the brass shaft specimen has a slightly bigger diameter than the diameter of the mild steel shaft specimen. Okay, for brass shaft, the angle of twist increases exponentially with the increase of load, and that is W. For mild steel shaft, the angle of twist increases slightly with the increases of load, and that is W. For brass shaft, when the load is removed constantly 50 Newton from 200 Newton to 0 Newton, the angle of twist only decreases slightly. Also, at load W is equal to 0, the angle of twist will remain at 30 degree instead of 0 degree before the experiment. Okay, next, for mild steel shaft, when the load is removed constantly 50 Newton from 200 Newton to 0 Newton, the angle of twist decreases until the angle of twist is equal to 0 when the load is fully removed. That is when the load is equal to 0 Newton. Okay, lastly, after the experiment, both the specimen are laid on the table. For brass shaft, one of its end of the flat surface was unable to lay flat on the surface of the table as before the experiment, whereas for mild steel shaft, both its end can still lay flat on the surface of the table similarly as before the experiment. Okay, that is for observation in lab torsion tests. Thank you.
Okay, Assalamualaikum warahmatullahi taala wabarakatuh. So today, my name is Muhammad Bayhaki bin Abdul Aziz. I'm from group 2. So today I will give explanation about the calculation on lab solid in topic torsion test. So I will show you the calculation. So for this experiment, we need to find torsion constant, that is J, for brass and mild steel. By using formula J equal to pi d the power of 4 over 32, we will get the answer after we insert the value. That is pi, and the diameter that is given over 32. Same thing goes to mild steel. We'll also use the same formula, that is pi d the power of 4 over 32. After we insert the value, we will get the answer. So the next thing is we need to find the shear modulus, that is G. G is equal to TL over J and angle of twist. T is for torque, L is for length, J is for torsion constant, and alpha is for the angle of twist. For brass, we need to find the torque, that is F times D. F is given and D is given. The length of the model is also given. The J we will get from the above calculation, and for angle of twist, 4 degrees times pi over 180 degree, because we need the answer in radians. So for calculation, we just insert the value into the formula. So next we will get the answer. This is 32.44 gigapascal. So for the mild steel, we'll also use the same formula, G equal to TL over J angle of twist. For mild steel, we'll also need to find the torque, that is 50 Newton times the distance. We will get the torque, the length is given, and J will get from above calculation, and the angle of twist we need to find it in radians. After we get those value, we insert it in the formula, and last we will get the answer. So the next thing is we need to find the shear strength. By using formula R angle of twist over L, we will find the shear strength. For brass, the radius is 6.09 over 2. 6.09 is the diameter, so for radius we divided it by 2. And then for angle of twist, we get it from the above calculation. So the length is given, and after we get all those values, we insert it into the formula, and we will get the answer. For mild steel, we also use the same formula, and that is shear strength equal to R angle of twist over L. After we insert the value, we will get the answer. Next thing, for shear stress. By using formula G and shear strain, we will get the shear stress for brass and for mild steel. G is obtained from above calculation, the shear modulus. The shear modulus of brass we already know, and the shear strain for brass we already know. We times it up and we will get the answer. Same thing goes for mild steel.
Discussion: when dealing with cross-section of shaft that is not cylinder, different formula in obtaining the shear stress, torque and angle of torus will be different. For bar of rectangular cross-section, the maximum shearing stress and the angle of twist for a uniform bar of rectangular cross-section and subjected to pure tension T are given by maximum shearing T max. T equal K T over K square AB square. Angle of twist phi equal TL over K2 AB cube G. Coefficient for rectangular bar in torsion. For thin wall member of uniform thickness and arbitrary shape, the maximum shearing stress is the same as for a rectangular bar with very large value of A over B and can be determined with K equal 0.333. Also, angle of twist can be determined with K to 0.333. The shearing stress at any given point of the wall can be expressed in terms of the torque T as equal T over 2T AB. Determination of external loads. Actual loads must be determined with reference to the functional requirement of the system. Some of the examples of typical loads applied to a shaft during power transmission include the torsional loads which appear due to torque being transmitted, transverse loads due to applied by many transmission elements, axial loads, twist and deflection due to bending moment. Selection of preliminary dimensions for shaft. Preliminary dimensions depend on the geometrical and functional requirement of the system as well as the bearing arrangement used for shaft support. The bearing should be placed as close as possible to the line of application of the load and avoid long cylinder shafts. Identify critical shaft sections. Critical sections are sections likely to be subjected to high stress. The critical sections should be located by inspection with reference to applied load. Since critical sections are usually associated with changes of shaft section or point of load application, thus when considering fluctuation loads, fractions which produce high stress concentration are particularly critical. For safety and better quality of shaft, it should be considered more than one potentially critical section. Conclusion: the exponential shear modulus G for brush shaft is 32.44 GPa, whereas the theoretical shear modulus G is 40 GPa. For mild steel shaft, the experimental shear modulus G is 65.46 GPa, whereas the experimental shear modulus G is 85.46 GPa, whereas the theoretical shear modulus G is 77 GPa. Steel is more elastic, which deflect a small angle of twist only when subjected to the same load, from 0 to 200 Newton as brush shaft. In addition, steel shaft is able to return to the original position upon the removal of the load from 200 to N. Meanwhile, brush shaft, which is less elastic than mild steel shaft, is unable to return to its original position, that is 0 degree of angle of twist after the removal of all the 200 Newton load, but with an angle of twist of 30 degree. This means that mild steel shaft has higher yield strength than that of brush shaft. There is a difference for the theoretical shear modulus and the experimental shear modulus G, as the less sensitivity of the protector division.